So we are still finishing up section 9.2. Again, test corrections due Wednesday, quiz on Wednesday, end of term Friday.
What?
Sorry, midterm Friday. End of term would be a little too soon.
That's awesome.
The fourth quarter is giant.
Okay, so we worked with the two forms that L'Hopital's rule works for. 0 over 0, infinity over infinity. Those are the only two forms L'Hopital's rule works for. But there are some forms we can rearrange. We call these indeterminate forms. Indeterminate means you can't determine it. So 0 over 0 we can't determine. Infinity over infinity we can't determine. So these are some indeterminate forms we could still apply L'Hopital's rule to eventually, but we're going to have to rewrite it first so that it's infinity over infinity or 0 over 0. Because it has to be in that form before we can actually then take the derivative. So we have infinity times 0, infinity minus infinity, 1 to the 0, 0 to the 0, and infinity to the 0.
Wait, is it 1 to the infinity or 1 to the 0?
1 to the infinity. Did I say 0?
Yeah.
Sorry. It is 1 to infinity. I wrote the right thing, said the wrong thing. Because what is 1 to the 0? That is something we can determine. 1. Anything to the 0 is 1. And that's a comma sign after the infinity minus infinity.
Oh.
So these are all, and I put a line around the ones with exponents because those all follow kind of the same way to rewrite. These are the forms that we could rewrite them somehow. There's going to be a couple of different tactics that we're going to use so that we can have 0 over 0 or infinity over infinity and then do L'Hopital's rule. I'm going to drag example 4 up so that we can see the rest while we talk about example 4. So we still start our process by checking to see what indeterminate form do we have. So everywhere I see x, I'm going to plug in infinity and see what's going on. We have infinity times sine of 1 over infinity. What's 1 over infinity? What's a very small number, in fact, so small it's 0. Any number, if it's just a number divided by infinity, infinity is so big it drives that division to 0. So we really have infinity times sine 0. And what's sine 0?
0.
0. So is it one of our forms that we could finagle so that we can actually apply L'Hopital's rule? I like that word, but for some reason every year I use it. It's finagle.
It's so weird.
Okay, so we want to rewrite this, and I'm going to focus on this letter x. I'm going to rewrite this letter x because we want a fraction involved somehow, right? So I'm going to leave sine of 1 over the x the same. But somehow I want a fraction involved because we know we want infinity over infinity or 0 over 0. I need that in order to be able to use L'Hopital's rule. So somehow I want to rewrite this x so that we get a fraction. Okay. So if we brought it to the bottom, that would be x to the negative 1, right? Right now it's x to the positive 1, but I want to bring it underneath. Anytime we move from one level to the next, we get a negative exponent. But to help us when we're trying to see L'Hopital's rule, I'm going to even write that a tiny bit different. This will actually be better for deriving, but for understanding that we can actually apply L'Hopital's rule, I'm going to write it as 1 over x.
Oh.
Because x to the negative 1 is 1 over that. So we took this x and we rewrote it as divide by 1 over x. It's the same thing. If I went through and solved this, I'd get back to x times sine 1 over x. We're just kind of being tricky. Usually we want to get to multiplication and get rid of fractions instead of put a fraction back into a problem. So now we check and see if L'Hopital's rule applies. So what do we say about 1 over infinity?
0.
0. So we have sine 0 over 0. Sine 0 is 0. So we get just 0 over 0 just by doing a slick trick by rewriting x as 1 over x. So now we can apply L'Hopital's rule. We couldn't apply with how it was written at first. Now we can apply L'Hopital's rule. So both of these I'm going to write as an x to the negative 1 for the deriving part. So we're writing a little more than we would really need for the problem, just because we're talking about it right now. But I'm going to rewrite it as sine of x to the negative 1 over x to the negative 1 so we can actually derive. So we take our derivatives individually. Derivative of sine x to the negative 1, ignoring x to the negative 1 on the bottom. So what's the derivative of sine?
Cosine.
Cosine. Derivative of the outside, evaluated at the inside, so still times x to the negative, or still of x to the negative 1, multiplied by the derivative of the inside. What's the derivative of the inside?
Negative 1x to the negative 2.
Perfect. Negative 1x
Remember to the 2.
to the negative 2.
You better slow down going back on too fast. Sorry.
So now what else do I still have to do to finish
The
L'Hopital's rule?
bottom.
Take the derivative of the bottom. What's going to happen when we take the derivative of the bottom? What do we get? Same thing, which is nice because what happens? Cancels out.
Oh, that's so wonderful.
That makes our life a lot easier. So, if we're going to apply our limit now, we plug in infinity. Cosine of, this time I'm going to rewrite back as 1 over. What did we say we mean when we have 1 over infinity?
It's 0, so it's
0.
Oh, so it's 1.
So cosine of 0. So, really, L'Hopital's rule still applied. We just had to do a little finagling. Rearrange some stuff. Okay. So, ultimately, our goal with most of these is to get a fraction. We need that fraction form of infinity over infinity or 0 over 0 in order to apply L'Hopital's rule. So we also have the possibility of having infinity minus infinity. Everyone fine if I turn to the next page?
No.
Too late now. Okay. Okay, so we have the limit as x approaches 1, of 1 over ln x minus 1 over x minus 1. So again, we tried plugging it in first because if it's just a normal limit, plugging it in will work. Which would give us 1 over 0 minus 1 over 0. And what do we really mean by 1 over 0?
Undefined.
Undefined. Or infinity. So we get our form infinity minus infinity. Again, that doesn't mean I can apply L'Hopital's rule yet. It just means there should be a way for me to rearrange this to apply L'Hopital's rule. So this one, what do you think we should do? What seems like a good tactic to start with? Turn to your neighbor. If you will group with Eliana now. And discuss what tactic do you think we should use? Okay, so Evelyn, what did you and Eliana say?
Find a common denominator.
Find a common denominator. That seems like a pretty good way to start. Because then I won't have two fractions, I'll have only one fraction. So, if I'm going to find a common denominator, usually we just multiply each fraction by the other one's denominator. So what do I multiply 1 over ln x by?
X minus 1 over x minus 1.
And what do I multiply 1 over x minus 1 by?
Ln of x.
So I get the limit as x approaches 1 of x minus 1 minus ln x over ln x times x minus 1. So now again, we check. We'd simplify first, but there's nothing here really that we can simplify. If it was all polynomials, we could probably find some stuff, multiply stuff out, combine like terms. This one, there's nothing to simplify, but if I plug in 1, I get 1 minus ln 1 over ln 1 times 1 minus 1, which gives me 0 over 0. Because what's ln 1?
0.
0. Something you should have memorized. You should know what ln 1 is. Just like you should know what ln e is. What's ln e? 1. So 0 over 0. I may apply L'Hopital's rule at this point. So we take the derivative of the top by itself. What's the derivative of the numerator? 1 minus 1 over x, good. Derivative of the denominator is going to be a little bit trickier. What do we have to use to find that derivative?
Product.
Product.
That's what it's called.
Yeah.
I don't have it like in my mind.
If it had ln of x minus 1, it would be changed. It's kind of weird because the ln x
Oh, yeah.
is next to the
I don't remember
parentheses.
the word
So
product, and I was like, this.
that thing. Yeah. As long as you know how to do it, really, you don't need to know the name. So second times derivative of the first plus first times the derivative of the second. So let's do some distributing. We get 1 minus 1 over x over x times 1 over x is 1 minus 1 over x plus ln x. So what's going to happen if we plug in 1?
Oh, we're gonna get 0, 0 again.
0 over 0 again, so we've got to do L'Hopital's rule again. So, take our derivatives. Really, 1 over x is the same as x to the negative 1. So we would get
X to the negative 2.
positive x to the positive, or
Oh.
to the negative second because,
Because it was already negative.
so x to the negative second over, same thing down here, x to the negative second plus 1 over x, because the derivative of ln x is 1 over x. So now what's going to happen if we plug in 1? What's 1 to the negative 2? 1. 1 to the negative 2 plus 1 over 1. and get 1/2. Okay, so that's our second trick. So our first trick was to rewrite x times something as that something over 1 over x. Our second trick was to combine our two fractions. Our third trick is a little more complicated, but we've seen it before when we've been doing derivatives. So this trick will work for any of the last three forms. That's why I grouped the last three forms together. 1 to the infinity, 0 to the 0, or wasn't it infinity to the 0 as the third one? Yeah. This trick will work for any of these last three. So for this trick, I need a left side. What do we usually call something like this? 1 plus 1 over x to the x. What do we usually have on the left side of something like that? If I said equals, I'm going to leave space for the limit, what would I usually put over here? What do I usually call any function that I'm working with? F of x. Or, to make it easier for us to work with, y. So we can call any function we're working with f of x or y. They still have their limits in front. But we've got to do something. Again, if we plug in, we really should check our form first. Sorry. Sometimes I get to the point where I'm like, I don't know what I'm doing. I don't need to check the form. But that's how they trick you on the AP test, is you not checking the form. Because you're like, hey, I know what I'm doing. I don't need to check the form. But that's why we really need to do it every time. Because in the AP test, they like to try and trick you. They like to make it look like you could apply L'Hopital's rule, but you can't really. So 1 over infinity, what did we say that was?
0.
0, so we get 1 plus 0, which is 1 to the infinity. Okay, I'm good to go use my slick trick to figure out a form so that it's infinity over infinity or 0 over 0. So, looking at this, we have a variable raised to a variable. We've got to think way back to when we were doing logarithmic differentiation. There is only one way for me to not have a variable up in here anymore. We want to use a property. Natural log, both sides. We're going to ln both sides. That's why we need a left side. I can't ln the right side if I don't have an equation. I can't just ln out of the blue. And this is going to affect our final answer. Because when we ln both sides, we've got to undo that at the very end. At the very end, we're going to have to e both sides. And that's something that's easy to forget. Don't forget
So gross.
to e. So we ln both sides. When we've natural logged something, what can I now do with that exponent?
Get rid of. Not get rid of.
Put it in the front. So we have limit as x approaches infinity of ln y equals limit as x approaches infinity of x times 1 plus, x times ln 1 plus 1 over x. So the left side, we're not going to do anything else with it until we're at the very end. So for now, we can ignore the left side. The right side, now I have a multiply. So if I plug in infinity now, I have infinity times ln of 1 plus 1 over x. What did we say? 1 over infinity. What did we say? 1? 0. 1 plus 0 is 1. So what's ln of 1? So we have infinity times 0, which means we've got to do a second slick trick on this. What do I have to do when we were multiplying? Rewrite it as 1 over x. So this left side's still here. You can keep writing it, or you can just make sure you don't forget about it. Limit as x approaches infinity of ln of 1 plus 1 over x all over 1 over x. So now what do we get if we plug in infinity? Zero over 0. So we are good to go and use L'Hopital's rule. We cannot use L'Hopital's rule until it says 0 over 0 or infinity over infinity. So now we take the derivative of the top and the derivative of the bottom and see what happens. Both of them, again, this is really x to the negative 1, which will help us for the differentiation. For the actually plugging in of the limit, it's easier to leave it as 1 over x. So we take our derivative. Derivative of the outside. What is the derivative of ln? 1 over x. So 1 over the inside. 1 plus x to the negative 1 times, I don't like the way I wrote that. I'm just going to, times the derivative of the inside. What's the derivative of the inside?
Negative x.
What rule did we just apply there?
The inside one.
Inside, outside one. Chain rule.
Yeah.
Would you take the derivative of the root of y also?
No. On the right side, the reason we can do it independently is because we're actually applying L'Hopital's rule. We didn't just say take the derivative of both sides. We're actually applying a property, a theorem of mathematics that says I can take the derivative of each. If I applied derivative to both sides, I would have to do quotient rule instead of take them individually. So what do we get when we take the derivative of the bottom?
The same thing.
Negative x to the negative 2. So I actually don't want to write it on top of the other fraction because then I can see a little bit easier that they cancel. So now we try plugging in infinity. Limit, or sorry, if we plug in infinity, we don't need the limit anymore. 1 over 1 plus x to the negative 1. So infinity to the negative 1. All of that would be 1. Why is that entire thing 1? Infinity to the negative 1 is 0. That's the same thing as 1 over infinity. It's just written a little bit different. So we have 1 plus 1 over 0, which is 1. That is not our answer. We have to think back to what we did to the other side. We have ln y right now. How do I get rid of ln? E it. We cannot forget, sorry, I'm running into my next example. I'll have to, in my next problem. We get y equals e to the 1, or just e. So you cannot forget to e at the end, because we always feel like we're done. We feel like we're finished when we get that 1. We're like, I took the limit. Hooray, I'm done. But we're not. Okay, so I'm going to have you guys try this problem, and then you'll have about 20 minutes for your assignment today since we split L'Hopital's rule into 2 days. It's not that all of them are, they're all pretty easy, but they're easy individually. If we try and cram L'Hopital's rule and all the ways we can rewrite in one day, it's just information overload.
Last night?
Okay, so when you're finished, this limit should equal 1.
That's true.
Your final answer should equal 1. I've checked most of your guys' answers, but if you're not quite finished yet, I'll come by and check it. But I want to put the assignment up so people can get started.